We're going to focus in chapter 10. In chapter 10, we were interested in pure substances. In other words, solids, liquids, or gases. Now we're going to look at what happens to the physical properties of combinations, mixtures of these substances. So again, the identities haven't changed of the substances. We're just mixing them together. And let's see. Let's do this. Now we're chapter 11 only. All right. In the first semester, we introduced the concept of solutions, I think. I hope we did. What does it take to make a solution? A homogeneous mixture is a solution. Excuse me. We typically think of solutions as some solid mixed in a liquid, like salt water or sugar water. But solutions, homogeneous mixtures, can be any combinations of phases. If we look on the right here, the solute and solvent are given. And remember, the solvent is the major component and the solute is the minor component. And by definition, we can only have one solvent, but we can have many solutes. So if we mix a gas together with a gas, we get a gas, and that's a mixture. The air we breathe is a solution. Natural gas that comes out of the ground is a solution of primarily methane, but it also has some other gases mixed in with it. Most notably, it has helium. Right? That's where we get our helium. We don't get helium from the atmosphere. It's just not enough of it to be economical to extract it. But from natural gas, the concentration is much higher, and we can separate the helium out, and that is used to be a strategic element. The government regulated its use because it was used in dirigibles. Anyway, if you mix a liquid and a liquid, you get a liquid, like antifreeze, booze, anything you can think of. Anytime you mix a liquid and a liquid and it produces a homogeneous mixture, then that's a solution and it would be a liquid. We talked about a mixture of solids and solids, brass, copper, and nickel. Bronze would be copper and zinc. Let's see. Say 14 karat gold, right here I have on my finger, is gold and usually copper, depending on what color you want. Mine's yellow gold, so it's probably copper, which is a mixture. It's a solution. If you mix a gas into a liquid, such as in pop, then you get a liquid. If you mix a solid and a liquid, you get a liquid. That is, as long as the solid is soluble in the liquid. If you mix a solid and a gas, which is a strange concept. Pardon me. Hello? Junk call. Okay. Yeah, if you mix a gas in a solid, you get a solid. The example here is hydrogen and platinum. Platinum is the catalyst. Hydrogen is one of the reactants. And usually, well, not usually, but could be, one of the other reactants is a an unsaturated fat. That is one that has lots of double bonds in it. And if you want to know more about that, take my organic chemistry class. But we saturate the fatty acid by reacting it with hydrogen and replacing those double bonds with hydrogen. It opens up the double bond and saturates the fat. This effectively gives the fat a much higher melting point and a much higher smoke point. But it's not very healthy for us. We've discovered that. But in order to get there, the gas has to be dissolved in the solid platinum. Okay, how do we, since solutions can have variable composition, that is, for a given amount of solvent, we can have a varying amount of solute. So how do we express that? Right? We need to be able to quantify that so that we can relate that to various properties. And these are the four that we're going to look at. There are other ways, but these are the four major ones. Molarity, and I'll define them in a minute. Mass percent, mole fraction, and molality. Okay, so let's look at it. Molarity. Molarity is simple. Moles of solute per liter of solution. Right? So if you're going to make a solution with a compound, say you put it in water, then you've got to calculate how many moles you're actually putting into that solution and how many liters are represented by it. The advantage to molarity is that if I know the molarity and I remove from the stock, I remove a certain volume, then I automatically can calculate exactly how many moles of solute I have. And here's an example. Say we put 1 mole of sugar in 125 milliliters of solution. What's the concentration in molarity? Well, first of all, you've got to know that molarity is moles per volume. Right? This is moles, and this is volume in liters. When you're calculating molarity with these values, the units must be moles and liters. Moles is good. We've got sugar in moles. We don't have volume in liters. So how many liters is 125 milliliters? If you work with volumes as long as I have, you know instantly that that's 0.125 liters. But if you're new to it, you can say this. We want to convert that to liters. So liters has to be here. Milliliters has to be here. What's the ratio, our conversion factor? Well, we have, for every 1 liter, we have 10 to the third milliliters, 1,000. So we're dividing 125 by 1,000, which means we move the decimal to the left 3 places. That's 0.125 liters. Now we can calculate molarity. And if we put those numbers in here, right, we get 8 molar. Okay. Recognize, though, that this formula for molarity is just that. It's a mathematical expression with unknowns, an algebraic expression. And if we know 3 of the values, we can calculate 2 of the values, we can calculate the third. Right? In this case, we're given molarity, and we want to know what volume is required to give us 2 moles. So we would solve for volume. Right? Volume over here, moles over molarity. And then we would just plug in the values since the values are uniform as molarity and moles. we can get the volume dividing 10 into 2, which would be 2/10 liter. Or how many milliliters would that be? 200, right? 3 places to the right. Here's another problem. Suppose we have 100 grams of each, sodium hydroxide, potassium chloride, and we dissolve each separately in 250 milliliters of solution. Remember, that's the total solution, not the amount of water that we put them into, but the amount of solution that we prepare as a result. That's an important distinction. What's the concentration of each solution in terms of molarity? Well, we have grams, we don't have moles. So if we have 100 grams of sodium chloride, we need to know how many moles that is. Pardon me for just a second. Come on. One of my cats wants to join the meeting. Come on, get up here. So we've got to convert them to moles and the volume to liters. The volume's easy. It's like 0.250 liters. But we have to convert grams of each into moles. So for sodium hydroxide, not sodium chloride. Or 100 grams of potassium chloride. Yes. Grams of potassium chloride. It's the same idea, but different values. Right. Sodium hydroxide would be, let's see, 23, 16, and 1.01. So this is 23, 16, and 1.01. So we add those together and we get 40.01. There we go. That'll give us moles of sodium hydroxide. Potassium chloride is probably heavier. Let's see, potassium is 39.1. And chlorine is 35.45. So that's, let's see. $74.55. Okay. So if I divide that number into 100, I get 1.341 moles of potassium chloride. And if I flip that, nope. Oh, I didn't put it in yet. Okay, so 100 divided by 40.01 is 2.499 moles of sodium hydroxide. Okay, so now we've got our units. All we have to do is calculate. So for this one, we've got 2.499 moles per 0.250 liters. And for this one, we have 1.341 moles per 0.25. And I think I have the answer already here. This is 10 molar. That makes sense. And this is, let's see, estimate for about 5.2 or thereabouts, 5.37. molar. So this is sodium hydroxide. This is potassium chloride. The point of this slide is we're working in molarity, we're working in moles, which means you can't use mass. The mass has to be converted. Mass percent, on the other hand, works directly from mass. So what would be the disadvantage? What would be the disadvantage to molarity? The disadvantage to molarity is in the denominator. Volume. Volume changes with temperature. So to be the most accurate value, your molarity has to be determined at a given temperature. Now, as a practical matter, for aqueous solutions, right, coefficient of expansion for water is relatively small. So within a range, say any room temperature is going to give you good values. But if you increase the temperature dramatically or decrease it dramatically, then you're talking about a change in volume that changes your molarity. Whereas mass percent, right, it's based entirely on mass. It doesn't matter what the temperature is, right? Mass doesn't change with temperature. So all you need is the mass of the solute and the mass of the solution, right? Which would be the mass of the solute plus the mass of the solvent would be the solution mass times 100%. And when we say mass percent or weight percent, it depends on the units. When we say percent by mass, we would do that. Simply because percent is a dimensionless number, right? And mass divided by mass cancels out. So there are no units. What we're saying is that it's parts per 100 parts. And we need to know what those parts represent. In this case, we're saying it's so many parts, mass, grams, pounds, whatever, per 100 grams, pounds. Okay. What's the percent by mass if you have 5.5 grams of glucose and 78.2 grams of water? The total mass is 5.5 plus 78.2. So we would divide, well, we're not showing you. We would divide 5.5 by 78.2 plus 5.5, which would be 83.7. So 5.5 divided by 83.7 times 100 is 6.6%. And I should have put mass here. Percent by mass. When I think we went over this in the first semester. When you're determining the empirical formula for a substance, bench chemists usually report in terms of mass percent, and we work from there. Mole fraction, on the other hand, the name gives us the formula. Mole fraction. It's a fraction of moles. Moles of the solute in total moles of the solution. So you have to be given, or you have to calculate the moles of each of the components of your solution. Here's an example. if we put 8 grams of hydrogen phosphate, which in water would be phosphoric acid, in 100 milliliters of water, what's the mole fraction? And we have to assume that the density of water is 1 gram per milliliter because we're given volume of water, not mass. So if we assume that the mass of the density of water is 1 gram per milliliter, which is just a little bit high, but for our purposes, it's okay. We have 100 grams of water and 8 grams of phosphoric acid. So we can calculate the moles of each one. Let's see, did I do it or just give the answer? I just gave the answer. Okay, so let's do it. 8 grams of hydrogen phosphate. We have to convert there. So hydrogen phosphate is 3.03 for the hydrogen. Phosphorus is 30.97. It's just one of them. And then there are 4 oxygens, which would be 4 times 16 would be 64. Let's see, that's in there. 8, and that's 98. Okay. Now we need 100 grams of water. Convert that. Right? So, what's the molar mass of water? We've done this so many times, you ought to just like that. 18.02 grams. Now we can calculate the moles. So let's see, 8 divided by 98.00 divided. This is 0.816 moles. Oops. No. My decimal's off. 0.0816 moles. And water is 100 grams divided by 18.02 is 5.5 or 9. Okay, so the mole fraction is going to be the total of these two. This will be the total, 5.631 moles. And then the mole fraction of phosphoric acid is 0.0816 divided by 5.631. That would be 0.0145. And that's a mole fraction, which means it's also a dimensionless number because moles divided by moles cancel. So if you see that number, it doesn't mean anything unless you're told that that is the mole fraction of this solute in that solvent. Okay, molality. Remember, the problem with molarity is volume. So molarity is moles per volume. Molality fixes that problem. Molality with a little m is moles per mass. Now, we have to stipulate what that mass means. This is moles of the moles of the solute. This is kilograms of the solvent. So there are 2 changes here. Volume is in liters of the total solution, whereas molality is mass of the solvent, excluding the solute. Okay. In most cases, they're very close together in magnitude, but the molality is stable if you're conducting an experiment where the temperature is changing. Then molality is preferred because it is impervious to temperature change. Okay. So I should have kept my information. Let's see. Phosphoric acid was what? It was 3.03, and phosphorus is 30.97 and 64. 98. So phosphoric acid is 98 grams per mole. If we want to calculate the molality, then we have 8 grams. I have to recalculate this one. 8 grams and 98 grams of mole is 0.08163 moles. Okay, so if we're going to calculate the molality of this solution, we have the moles of the solute. We need the mass of the solvent. 100 grams is how many kilograms? Actually, it's a tenth. It's 1/10 of a kilogram. So the molality of this solution is 0.08163 divided by 0.100 kilograms. All right. So that's easy. Yeah, it should be 0.816 molal. Right. Dividing by a tenth is the same as multiplying by 10. All right. So now that we have ways of expressing the concentration, the composition of a solution, I want to talk about how solutions form. Now, this is a theory. This is a proposed mechanism for the formation of solutions. All right. And these are the 3 steps. I think I'm going to draw them on the board instead. All right, I'll leave that there and do it up here. Okay, so you have the solute here. You have the solvent here. And you have the solution here. Okay. What has to happen in order for the solute and the solvent to become mixed, to experience their intermolecular attractions? Well, first of all, you have to break the bonds, the intermolecular bonds of the solute. So here we're break bonds. And those are intermolecular bonds. Those are not chemical bonds. You have to do the same thing for the solvent. Sometimes we call that make a hole. So you break the bonds of the solvent molecules from each other. Now, when you put them together, they form bonds between the solute and the solvent. Right? So here you're forming bonds. Okay. Now, in terms of energy inputs and releases, you have to put energy into the solvent to break those bonds. This is endothermic, right? Delta H is positive. That costs you energy. Same thing over here. Oops. Okay, so let's call this one delta H1. This is delta H2. Now, when you form the bonds, they're at higher energy. Form the bonds, you decrease the energy. They give up energy. So this is an exothermic process. So delta H here, 3, would be negative. Okay? So what we actually measure, actually we can measure all three. We just can't measure them in the formation of the solution. We can devise experiments where we can measure individual processes. But when we form the solution, the combination of these three, the linear additive combination of these three, determines whether the overall delta H of solution is going to be exothermic or endothermic. And that's what we're trying to show here. You got to put energy in, and then you get energy back. And the enthalpy of solution is the summation of these three processes. Now, if we have to put more energy in than we get back, then we're going to decrease the temperature. It's going to feel cold. But if we get more energy back than we put in, then it's going to feel hot. And anybody who's ever worked in and around a hospital or been a patient in the hospital, you need a hot pack or a cold pack. The nurse will go away and come back with this bag, and it's got a little container inside of it with a salt of some kind, a compound. And they'll break it and then mix it together, and it'll get cold or hot depending on whether it's a hot or a cold pack. And it's you're experiencing at that point this process right here. Okay, I've already talked about that. And I've talked about that. This is just a diagram showing what's happening, right? Energy separate to energy of separated. If we add energy, we add energy to break up the solvent and solute, and then we get energy back, and the total is this difference. This difference here means that it's exothermic. It goes more negative, which means exothermic. This one example goes positive, which means it's endothermic. Okay, now let's see if we can use this information to draw conclusions about why certain solutes and solvents mix and why some of them don't. The rule of thumb is like dissolves like. Right? So polar compounds, polar solvents dissolve polar solutes, and non-polar solvents dissolve non-polar solutes. All right, here's the layout. Say we have a polar solute and a polar solvent. So the delta H1 is for the solvent, right? Takes a lot of energy to break the bonds of a polar solvent. And it takes a lot of energy to break the bonds of a polar solute. And when we combine them, right, put them together, then we get a large amount of energy back. We put in a large amount, we get a lot back because we got polar breaking, then polar combining. So we get a lot of energy back. The delta H in this process is small. A solution is expected to form. If we have let's go down here to nonpolar solute, nonpolar solvent. A nonpolar solute takes very little energy to break apart. A nonpolar solvent also takes a little bit of energy. So when we put them back together, we don't get much back. Very small delta H, a solution forms. This case, where we have a nonpolar solute, it takes very little energy to break it apart, but it takes a whole lot of energy to get the polar solvent apart. When we put them back together, the polar and the nonpolar don't interact. Right? The London dispersion forces on the solute don't interact well with the ionic or the polar nature of the solvent. So if we put a lot of energy in, then it takes a lot of energy, positive energy, that we've lost. This is a huge cost. That's why we put this positive here. We put that energy in and we didn't get anything back. We don't expect the solution to form in that case. The same logic applies when the solute is polar and the solvent is nonpolar. Right? We put a lot of energy into the polar solute, not much into the solvent. We get very little back, and we have this large positive value. No solution forms. So the moral of this story is, when you have a small delta H, and this can still be cold or hot, right? We're talking about huge amounts of energy here. When this is very small by comparison, then a solution is expected to form. And that leads us to the rule of thumb, like dissolves like. Now, we didn't say a whole lot about probability. One factor that favors the process is an increase in probability of the state when the solute and solvent are mixed. I'm going to kind of leave that one alone for now. Probabilities are a difficult concept for most students. Processes that require, now you can grasp this one. Processes that require large amounts of energy tend not to occur. So if we put energy in but we don't get much back, then now another possibility, let's practical application. Say a nonpolar solvent is water. Excuse me. No. Polar solvent. Polar solvent is water. Nonpolar solute is the grease on your engine block. So you go to have your engine steam cleaned, right? You're restoring an antique car, and you need to steam clean the engine. So you take it to a service station that has the equipment, and they will steam clean it. Well, at first, you may think that all you have to do is get the grease hot enough and it'll drip off. But what we've discovered is that if you get that polar solvent, water, hot enough, right, it's virtually steam, then you can dissolve that oil in the water, right? So if you do have the ability to introduce a large amount of delta H, in your solvent, you can produce a solution temporarily. And then as the water cools, all that grease comes out and it drains down into a bucket. So these are generalities. Just because we say a solution doesn't form doesn't mean it can't form if the conditions are right. All right. So we're going to look at some experimental procedures and effects. First, we're going to look at structural effects, that is polarity, in terms of their effects on solubility. Then we're going to look at Henry's law, which addresses solubility of gases and liquids. Then we're going to look at temperature effects that and focus on aqueous solutions. So, structural effects, right? When we say like dissolves like, we say a polar solvent and a polar solute are going to easily form. And a nonpolar solvent and nonpolar solute are easily going to form a solution. The terms that we often use are hydrophobic for nonpolar substances. That just means water fearing. Phobia is a fear and hydro is water. Hydrophilics are those that love water, polar substances. The pressure effects, Henry's law is measures the effect of pressure of a gas on the solubility, or how much of it will go into solution. And as a general rule, as the pressure increases, the concentration of the gas in the solution increases also. Right. So we have this concentration of the dissolved gas equals pressure times some constant. Now, we may not, the constant is unique for each solution that you want to form. So a more useful form of it would be like we did with the gas laws. I'll take you back to first semester. If we say, let's rearrange this. C over P equals a constant. Right? So all other conditions being equal, if we have this set of conditions and this set of conditions, these are equal to the same constant, which means they're equal to each other. So we can do a before and after experiment, just like we did with gases, like Boyle's law, Charles' law, Avogadro's law, combined law. We can do a before and after scenario with Henry's law as well. Now, to interpret what is actually happening, we can use the kinetic molecular theory of gases. And we find that if we increase the pressure by decreasing the volume, we are increasing the number of impacts of the gas against the surface of the liquid, which means there is a higher probability that some of those molecules will dissolve in the gas. In the solvent. So that's why when you open the cap on a bottle of pop, it goes, you're releasing the pressure, which allows some of the gas to come out of solution. There's a head pressure built up in the space above, and some of that sound is going to be pressurized gas in the head space, and some of it's going to be gas coming out of solution. Now, temperature effects are another story. It depends. If you're talking about a solution that's made from a solid in water, most often the solubility of the solid will increase with an increase in temperature. Right? You can put more solid into solution as the temperature increases. And that's the logic there is that you're increasing the temperature of the solution, the solvent, which adds kinetic energy to the solid that's being placed in it and helps break the solid up, right? We're putting energy into that solute and breaking those bonds. However, this doesn't always occur. Sometimes a solid is more soluble as you decrease the temperature, and we're not really sure why, but it is a measurable effect. On the other hand, when you dissolve a gas in a solvent, the gas is always more soluble when you decrease the temperature. The reason for that is the water can hold more gas if the kinetic energy of the gas molecules is decreased. Right? They don't have enough energy to escape. So there's more of them that can be dissolved in the liquid. If you increase the temperature, you increase the kinetic energy of those gas molecules and they go into the gas phase. So that's why I take my pop, I put it in the refrigerator for a couple of hours before I crack the top. if I do it at room temperature, or if I'm at a picnic on a bright sunny summer day and somebody opens a 2-liter bottle of pop that's not been cooled, then it'll go whoosh, you lose half your gas. And the carbonation is half of the effect of pop. So that's why I cool mine down before I open them up. And you keep most of the carbonation in the water. The other advantage is once you seal it back up, you haven't lost all that gas, stick it back in the freezer, and it stays fizzy longer. All right. So here's the solubility of solids as a function of temperature. Notice that sugar becomes more soluble. All the nitrates become more soluble. All the bromides and chlorides become more soluble, but the sulfates become less soluble with temperature. It's not much, but it's measurable. Their solubility decreases with temperature. Whereas the solubility of gases decreases as the temperature increases. Now, it varies from one gas to the other. Right? Methane has a very high solubility at low temperature, and then it decreases considerably. Helium seems to have the flattest curve. And we used to use that fact, its solubility is very low, to prepare solvents for our liquid chromatographs. Solvents in a liquid chromatograph, the high pressure or the high efficiency, they go into the machine and they're pressurized to dozens of atmospheric pressure to drive that solvent through the column. Well, if you have any dissolved gas in your solvent, when the pressure is released on the other side, that gas goes poof, and causes your detector to go haywire. So you want your solvent, your mobile phase, to be gas-free or have very little gas in it. So what we would do, there are two ways to do this. You can put a vacuum on it, right? Decrease the pressure, and you suck all the gas out. Or it's cheaper to put one of these air stones that you see in aquarium and hook up helium to it. Put that down in your solvent bottle and bubble helium through it. It's called sparging. What it does is displaces all the other gases. And since it's very, very low solubility, it doesn't give your detectors any fits. All right. Now, What happens to water in a closed environment? Well, it produces a vapor pressure, right? So in this bell jar, if it was only a jar of water, a beaker of water, it would produce a certain pressure, like I think it was 24 torr at room temperature. But if you put the water in there with an aqueous solution of a non-volatile solid, like sodium chloride or any solvent, any solute, what you find is that the water is leaving both solutions, but it's leaving the water faster, right? The vapor pressure, and we're going to look at this in detail in just a minute. The vapor pressure over a solution is lower than it is for the pure solvent. So you get more water moving out of the pure water and setting up an equilibrium with the solution that draws water from the headspace and puts it in solution. So eventually, all the water is gone and you have more solution. There's a very dramatic effect if you put over here a concentrated solution of sulfuric acid. It will draw water away so fast that in just 2 hours, 3 hours, all the water will be gone. It'll be over in the other beaker. Okay, so I was talking about vapor pressure differences for pure substances, pure solvents, and solutions. The solution has a lower concentration, a lower vapor pressure than the pure solvent. And Raoult's law is the way we quantify this effect. So if we know the vapor pressure of the solvent, the pure solvent, that's what that little circle means under standard conditions. The pure solvent, we know the vapor pressure. If we can calculate the mole fraction of the solvent, then we can determine the vapor pressure of the solution. It's very simple. Now, this particular equation is only valid if the solute is non-volatile. It cannot exhibit any volatility at all. The only volatility comes from the solvent. If, however, we have a mixture of two volatile substances, solvent and solute, then we have to modify the equation. Right? Okay. This is a perfect obedience to Raoult's law. As the mole fraction of the solvent increases, that is, the concentration of the solute decreases, so the mole fraction of the solvent increases, we go from zero solvent, which gives us zero vapor pressure, up to pure solvent. That will give us the pure solvent vapor pressure. And along in here somewhere, if this is ideal behavior, you will get a measurable vapor pressure that can be calculated from Raoult's law. Now, if you have a mixture of volatile liquids, they form a good solution, but they have their own individual differences in vapor pressure as pure substances. What you have to do is use this modified Raoult's law. So we have, in order to find the total pressure, we have to find out what is the contribution of the vapor pressure from substance A, or could be the solute, and what's the contribution from substance B, the solvent. If we get ideal behavior, then you'll get a straight line between the two pure substances. And I've got a graph on the next page. So this one on the left shows ideal behavior. The partial pressure as the concentration of A increases will increase, right? Partial pressure increases until it reaches this point. And that would be the pure substance A, and there's no B in it. Go the other direction. As we increase the mole fraction of B to the left, then its line says from 0 to the pure substance B will give you that pressure. If they're ideal behavior, if they're perfectly ideal, then the connector between the pure B and the pure A gives us the combined vapor pressure for mixtures at various amounts of each one. Okay, that's ideal behavior. If, on the other hand, you have a difference in attraction between the solvent and the solute, then you can get deviations from ideal behavior. You can either get an increase in vapor pressure or a decrease in vapor pressure at any composition. Now, an increase in vapor pressure says that the solute and the solvent interactions are very weak. So that means there's less attraction for them in the solution. That means there's more for them. There's more vapor pressure from both of them because they don't attract one another. They say, well, I'm not staying here. I'm getting out. So they go into the vapor phase. And that increases the vapor phase. We'll look at some examples in a minute. If, however, you put them together and there's a strong attraction between the solvent and the solute, you get a concave deviation. This is a convex deviation. This is a concave deviation. The concave deviation means that they're strongly attracted to one another and they depress individual vapor pressures that combine to the total. Now, what circumstances will lead to that? If we look at the interaction, let's see the way the thing is coded here. The interaction of A and B, or whatever they are for each one, if we combine them and they're roughly the same interaction, then we get an ideal behavior. Okay, if they're individually attracted to one another, if they're attracted to one another with the same force that the pure substances are attracted to themselves, then we get an ideal curve, and that's a straight line connector. Examples here are benzene and toluene. Benzene is like this. It's a 6-membered ring. These are carbons, and then you have hydrogens. Right? Toluene, on the other hand, is simply this. There's a methyl group there. There's not much difference between the two, right? Nonpolar, nonpolar, very nonpolar. So their attraction in solution is about the same as it is as independent pure substances. Now, if the attraction is greater than they are as separate pure substances, then we get a negative deviation, the concave. Now, what we're trying to do is explain why. So think back to our 3-step process for forming a solution, right? We have to break these bonds, and we form these bonds. So if these attractions are stronger than they are for those, this should be an exothermic reaction, right? And the change in temperature should be an increase. And as a consequence, the attraction is so strong Example here, acetone in water. They're so strong that you get a negative deviation in the vapor pressure. Water's like this, and acetone is like this. So acetone is not as polar as water. Right? There's some polarity here, but this is very polar. But when they interact with one another, there's a very strong interaction between this polar and this polar. And that's what causes the negative deviation. Now, for this example, we break the bonds, and then we don't get much energy back when the solution forms. So this is an endothermic process, and the temperature change is negative. And we get a positive deviation here. This example is ethanol and hexane. Hexane is very nonpolar. Ethanol is slightly polar, right? Because you have that OH group on the side giving you hydrogen bonds, but they don't interact very strongly. Right? So that increases the vapor pressure above what we would expect. That's a convex deviation. Excuse me. So for each of the following solutions, would you expect to be ideal, positive deviation, or negative deviation? Well, let's look at hexane would take very little energy to break apart. Chloroform is slightly polar. So I would expect the interaction to be, excuse me, stronger than the individuals. So that should be a positive deviation, I think. Let's see, does it give me the answers? Doesn't give me the answers. Okay. Ethyl alcohol and water, it takes a lot of energy to break those apart, but you get about the same amount back. So this should be fairly ideal. Hexane and octane, you know what? I think hexane and chloroform should be a should be like acetone in water, a negative deviation. Yeah, their interaction is stronger than the individuals, whereas these are about the same interactions, so they should be ideal. And then hexane and octane, hexane and octane should be relatively equal also. So if they're equal, they should be ideal. Yeah, they're more like benzene and toluene, where ethanol and water should have a very strong attraction. They should probably be negative deviation, and hexane and chloroform will probably be a positive deviation. They won't interact very well. Okay, so positive, negative, ideal. I need to modify this slide so I don't have to stumble. Okay, we're coming down to the end. We got about 20 minutes left, so we'll have to talk about the lab next week. What is a colligative property? Colligative properties are those of solutions that depend only on the number of solute particles in the solution. It doesn't matter what those particles are, just the numbers of the particles. So their identity is immaterial, at least under ideal circumstances. Boiling point elevation, right? Everybody knows that one. When you put antifreeze in your car, it does two things. It keeps your fluid in the engine from freezing in the winter, and it keeps it from boiling over in the summer. So the boiling point elevation, it increases the boiling point of the solution by adding ethylene glycol. And it keeps it from freezing. It depresses the freezing point in the winter. Osmotic pressure, we'll define that in just a minute. Everybody has heard of osmosis. If you've had a biology course, you know about osmosis. So I'm not going to talk about that one right now in detail. Vapor pressure. Vapor pressure is a colligative property. And in fact, we've already talked about that one. That's Raoult's law, vapor pressure. So we're going to focus on these three right here. We've already covered vapor pressure. All right, boiling point elevation. Any non-volatile solute elevates the boiling point of the solvent. So we know what the boiling point of the solvent is. Then we measure the boiling point of the mixture, the solution, and we determine the difference. That's what delta T is, the elevation. And we only want to know the absolute value. We don't have to pay attention to negatives here. So when we do delta T is dependent upon this constant value here, the boiling point elevation constant for the solute, the solvent, and the molality of the solute. Okay? So, as a practical matter, what we would do is we would measure the boiling point of the pure solvent. Then we would add a known amount of solute in the form of, and we would know the number of moles, determine the number of moles, and the mass of the solvent into which we're putting the solute. We determine that molality. And then we have a constant that is peculiar for the solvent. Right? So this is like any other equation. Once you know two of those, you can figure the other one. So if we know the change in temperature and the molality, we can determine the constant. If we know the change in temperature and the constant, we can determine the concentration. That's the more useful one. The concentration of the solute in the solvent. And we don't have to know what the solute is. So remember way back when we were doing, when we were calculating empirical formulas and molecular formulas, we needed to know, to go from empirical to molecular, we needed to know the molar mass of the substance. This is one way to determine it, because we don't have to know anything about its molecular formula. Right? This method gives us a handle on the molar mass, the number of moles that are placed into a known amount of solvent. And if we know the number of moles that went into that solution and we measured it mass first, then we have moles per mass. And we determine the moles by determining the molality of the solution. So if we know these two by experiment, we calculate this one, which is moles per kilogram, and we know the kilograms of the solvent, right? Then we can determine the moles of the solute. And when we put the solute into the solution, we weight it. We know what its mass is. So now we know moles and mass. We can determine the molar mass of that substance. Okay. Boiling point elevation. So the temperature is going to increase when we add some solute. Freezing point depression goes the other way. The freezing point is going to decrease as we add solvent. And one of our experiments is using this technique. We have a similar formula, but in this case, the change in temperature, and I should do that, the absolute change in temperature has a different freezing point depression constant for the same solvent. Right? It'll be 1 for the boiling point elevation and a different number for the freezing point. And then we have the molality of the solute. So it's a similar type of experiment, only it's easier to perform than boiling point, freezing point. We're going to use, let's see, lauric acid, which is a fatty acid, as our solvent, and benzoic acid as our solute. And we're going to experimentally determine the molar mass of benzoic acid. Okay. Now, here's an attempt to try to describe changes in boiling point and freezing point of water. The vapor pressure of pure water is here, right? Because that goes from, let's see, this is solid, liquid to gas right here. So this is the equilibrium line for vapor pressure of water. This is vapor pressure of the solution. Notice that when we put something into solution, it decreases the vapor pressure, right? We've already determined that. So this line is going to be lower than that line. This line is a change from liquid to solid. So this line is the freezing point line. And we've already determined from our previous discussion, that the freezing point is going to be depressed, right? So the freezing point is going to be lower if we add a solute to it. So these are the two freezing point and boiling point lines as we've described previously. And we didn't talk about this one, the sublimation line, but it tends to be a little lower also. What we've got here is this change between pure substance and mixture is this freezing point depression. And between this substance boiling point at two different concentrations, this is our change in boiling point. So that's the theoretical basis for the colligative properties we've discussed so far. All right, I'm fixing to run out of time. Let's see. Hold on a second. All right, I'm going to go quickly through these. In this case, we're dissolving 25 grams of glucose in 200 grams of water, and the molar mass of glucose is 180.16. What's the boiling point of the resulting solution? Glucose has to be non-volatile, and it's a molecular solid, so it doesn't break apart. And you would take, I'll set it up for you. How about that? We won't do the complete solution, but I will set it up. So what's delta T? Delta T, and this is boiling point. Delta T for the boiling point is equal to, and this is absolute, so final minus initial temperature equals whatever the K is. In this case, it's, they don't tell us. Oh, we have to look it up. What's the boiling point depression constant? Boiling point elevation constant. So you can find it first. Just Google it. So I say boiling point elevation constant. And let's be specific for water. The solvent is water, correct? Yes, the solvent is water. So I'm going to say water. All right. And artificial intelligence is working. 0.512. So this KB is 0.512 degrees C per molal. Okay. And we have to determine the molality by finding the number of moles, molality, the number of moles of glucose, right? So we would have 25 grams per mole, and that would be 180.16. And this would give us the number of moles that would be divided by the kilograms of solvent, which would be 200 grams is 0.2 kilograms. So that value goes in here. Okay. So we got that value, we got this value, we've got what's the boiling point of the resulting solution? Oh, well, the boiling point is 100, right? So we're elevating, boiling point elevation. So the initial is going to be 100, and this is our unknown. Okay. So the difference between those two is 0.35 degrees. So the boiling point now is going to be 100 plus 0.35. Okay. One of the problems we encounter with this technique is traceable to solutes that dissociate in solution. In other words, like sodium chloride. If we put 1 mole of sodium chloride in aqueous solution, how many moles of ions do we get? 2 moles. So the Van Hoff factor is introduced into this equation. Delta T, boiling point, equals I times KB in. That I is the correction factor. If we know we have 1 mole of sodium chloride, then the correction factor would be 2. Now, it can go both ways, right? It can go 2, 3, 4. It can go up, or it can go down. It can go to 0.5. So what would cause that? Decrease the number of moles in solution. In solution, that would mean that the molecule that you put in there associates with one of its neighbors, one of the other molecules, and decreases its molality. So that would be a factor of, I don't know, 0.9, 0.8, 0.7. It does occur. Most of the time, it's a positive. It's a whole number. What would change also would change the value of I, the Van Hoff correction factor, is if those ions, once you get them in solution, some of them pair up. Right? If the solution is dilute, low concentration, this rarely happens. So you can use the full Van Hoff correction factor. If the concentration increases very high, then you have more opportunity for those ions to pair, and they decrease the molality of the solvent, solute. So in that case, say if you have a very high concentration of sodium chloride, the correction factor would not be 2, it might be 0.95. 1.95. But typically and ideally, that you just have to see how many ions break apart from the solvent, solute. So this would be 2 ions, this would be 2 ions, this would be 4 ions. 3 and 1 is 4 to give you your Van Hoff correction factor. I mentioned this already. And this is the modified equation, and this particular problem will take time. And I don't even know why I put it in here because it's very, very involved. It uses lots of information that we've covered, but you haven't had a chance to develop the calculating skills yet. So I've got it in here, and I've got it animated so that we can take 20 grams of sucrose and sodium chloride mixture. We don't know what the concentration, the relative amount of each one is. Right? And we put that in 1 liter of water, right? 1 kilogram of water. The freezing point of this solution is found to be 0.426. So it's depressed by a change of 0.426. That's your delta T. What we want to find is the mass percent composition and the mole fraction of sucrose in the original solution. So we need a little algebra. These are the given values. And on the next page, here we go. We have to, I'm running out of time. We have a total mass. We have the change in temperature. We're going to let the mass of sucrose be X because we eventually want to calculate its concentration. That means the molar mass of sucrose is calculated, and the moles of sucrose is X divided by that value. So the mass of sodium chloride is 20 minus X, and its moles is 20 minus X over 58.45. So the molality is going to be the moles of sucrose plus the moles of sodium chloride divided by 1 kilogram. Okay. So now we find that the Van Hoff correction factor for sucrose is 1, but it's 2 for sodium chloride. So there's a fly in the ointment. So we have to separate these calculations using the freezing point depression constant for water of 1.86 degrees C per molal. And this is our delta T, right? Our delta T is equal to correction factors times the molality times the K value, right? Only now the correction factor has to be modified because this is the number of moles of sucrose. This is the number of moles of sodium chloride. We have to apply a 2 factor for that one. And we know that the let's see, do we know that? 0.2290? Where did I get that? Oh, we solved this equation for I times M, and that's 0.2290. So we divided this value by that value. That's where this one came from. So this IM is split into 2 parts. One part is for sucrose. The other part is for sodium chloride. And this term here is equal to this term right here. So now that we have this equation, and that's the trick, going from here to here, the equation, we can tell how much is X. And we solve for X. X is 14.55 grams. That means sodium chloride is 5.45. And we do the calculations for percent, and we also do the calculations for mole fraction. Okay. Let's see. Okay. Osmotic pressure. I'm going to skip this one for now. We can calculate the osmotic pressure by, well, I shouldn't skip it because here's the equation. The equation for osmotic pressure is simply, no, that's not it. This is freezing point depression. All right, I got my slides mixed up. That shouldn't be there. Plant cell has a natural concentration of 0.25 molal. You immerse it in an aqueous solution with a freezing point of 0.246. Will the cell shrivel? Oh, That is a valid question. What we have to do is find out what's the concentration in the solution outside the cell. That's what we were doing here. 0.132 molal based upon the freezing point, the freezing point depression. Okay, so now that we know the concentration of the solution outside the cell, we can draw a conclusion. Will the cell shrivel or will it explode? Well, the concentration inside the cell is greater than it is outside the cell. So water is going to flow into the cell and it should explode. Since 0.25, that's not right. That's inverted. That's wrong. The water is going to move into the cell. That should be the other way around. Water will move into the cell and the cell will explode. And it's due to osmotic pressure. So that was a lead in to osmotic pressure. Okay. I think I'm out of time. 12:20? Yeah. Okay. I'm almost to the end, so I'm going to finish. If you have to go, then I don't know where you're going to go in this weather. Yeah, it's still a mess outside. So I'll just keep talking as long as the power and the internet cooperate. The equation for the osmotic pressure as a function of molarity of the solution. So we use pi as our symbol for osmotic pressure, and osmotic pressure is in atmospheres. Then the molarity of the solution is M, and the gas law constant is R, and the temperature is in Kelvin. Okay. Now, since we are including temperature in the calculation, we can use molarity. And the gas law constant is it on the next page? Gas law constant. Where is it? Yeah, that's what I thought. I was just confirming. Gas law constant is going to be the one with atmospheres in it. 0.08. 206. So osmotic pressure is not dependent, well, it is dependent upon temperature. It's directly proportional. Okay, what do we mean by osmotic pressure? Well, there are a number of ways we can present this in the form of a illustration. But it's best to focus on the membrane. We have a pure solvent outside the bulb. We have a solution inside the bulb and a membrane separating the two. Now, we've set this up so that the membrane is semi-permeable. That is, it will only pass water. Only water can go through that membrane. So, if we have a situation where we have this membrane and we have a solution inside and a solvent outside, think of it in terms of the kinetic molecular theory. What's happening at the membrane? Well, you've got things bouncing on it. You got molecules hitting it, right? And if the pore size is right, only the water molecules will go through. Right? So with the solvent, you have impacts on that surface, right? From the solvent. And the solvent is water. On this side, you have fewer impacts on the surface because the solution incorporates a solute that can't pass through the membrane. So you have possibly an equal number of impacts, but only the impacts of water will pass through the membrane. So I'm only going to put the water impacts. So they're like this, like that, like that, like that. Right. So which way is the net movement of water going to be? The net movement is going to be this way because there are more impacts on this side. So when that happens, you increase the amount of water and you dilute the solution, right? So as you're going, you're diluting the solution. You're also building up pressure as this as the level rises. You build up a pressure there, and that pressure contributes to more impacts, right? So we're increasing the impacts of everything on this side inside the bulb. So if you're increasing the number of impacts on the inside the bulb, you're increasing the number of water molecules moving through. So at some point, the pressure itself causes more impacts of water to occur so that you get equilibrium. The rate of movement of water reaches a point when you have a sufficient pressure on this side, reaches a certain point where you get an equal movement of water in both directions. And it stabilizes at that point. That is a measure of your osmotic pressure. The distance between the surface of the liquid solvent and the solute inside the vessel. That's a measure of osmotic pressure. Okay, here's another way to do it, but it's the same idea, right? And the osmotic pressure is the difference between the two sides. This is pure solvent, this is the solution, and the same argument can be made. When you focus on the membrane, then the construction of the vessel doesn't matter. All right, osmotic pressure is also susceptible to Van Hoff correction. And for the same reasons and calculated the same way. So in this problem, I don't know, did I work it out? Yes. Okay, so if we have this 33.4 milligrams of compound dissolved in 110 mils of water at 25 degrees, the solution has an osmotic pressure of 558. What's the molar mass of this compound? Okay, so with that formula, we're given this one. We know that one. We're given this one. We can calculate its molarity. And if we know the molarity and the volume and the mass, we can derive from that the moles and calculate the molar mass. So that's where we're going. Right. So here are the values that we're given. We place them in the atmospheres here, right? We had 588 torr is, osmotic pressure of 588 torr. We have to convert that to atmospheres. So that's what this does. Then there's the molarity. There's the gas constant. And here's your temperature in Kelvin. And the molarity is 3.164 times 10 to the minus 2 moles per liter, or molar. Then we take that value, and we know that concentration is molarity times volume. If we look at the formula, M equals moles times volume, then M times V equals moles. We can calculate the number of moles in that solution. So when we do that, we find this is the number of moles. We have this many, 33.4 milligrams is 0.0334 grams per mole, and we calculate molar mass. All right. This was a curiosity that I had, and I've had since I was a kid. When I learned as a kid that there were trees in California that were 300 to 400 feet tall, and I started experiencing things in the sciences, getting information and saying, this is what happens in a tree. You know, the water moves up the xylem and feeds the leaves. But once I realized that if you make a barometer using water instead of mercury, you can only get the water to go 33 feet high. That's as high as it'll go, no higher. So I say, well, if that's the case, even if there's a vacuum in the leaves at the top of the tree, they'll never make it there. Not with that effect, right? Not with air pressure alone. So I was entertaining the idea that maybe there's a pull, right? The leaves are evaporating water, and you got this inside the cell. You got the stomates here. Let's see. Let's do like this. With an opening here, and the gases come out. Water vapor comes out, and inside the cell, you've got a surface here of water. And as it evaporates, the sides of the cell hold on to it, and it depresses like that. You lose some water. And the surface tension pulls it back flat. So that pulls on the water below it and pulls the water up the tree. Well, that turned out to be false. Experiments were done which tested that idea, that hypothesis, and found to be false. It doesn't work. So the last possibility, which I determined does work, is osmotic pressure. In the roots, the cells have a very, very high concentration of solute. And outside the roots, the concentration of solute is much, much lower. So the water is going to move into the roots and build up pressure inside the roots and inside the xylem. Well, the question is there enough pressure? So we have to measure what is the pressure, osmotic pressure, in those roots. So we use microprobes, and we go in and we measure it. Turns out to be that it can exceed, this is like a minimum, it can exceed 20 atmospheres. That's a huge osmotic pressure. 20 atmospheres in these trees. All right. So I said, okay, is that enough to go to the top of a tree? Okay. So first thing I did was find out how tall is that tree in millimeters. So I do 300 feet and change it to this many millimeters. And then I change atmospheres to millimeters of water. So this is 20 atmospheres. This is millimeters of mercury. And then this is the density conversion for water versus mercury. 13.56 millimeters of water is equal to 1 millimeter of mercury. And that conversion gives me 10 to the 5th millimeter column of water. Well, that's plenty big. That is 10 to the 5th versus 10 to the 4th. There is enough osmotic pressure in the roots to push that solution all the way to the top. All right. Oh, I forgot. We got to talk about colloids. What is a colloid? We talk about solutions. And solutions are homogeneous mixtures. Colloids are kind of a second cousin to solutions. They appear to be homogeneous, but the suspended particles remain suspended in the colloid because of their size, not because it's a physical interaction, not because of their bonding interaction with the solvent. So the particles have to be small enough so that the kinetic energy of the suspending medium impacting them will keep them suspended. All right. It appears to be a fine distinction, but it's real. And these colloids can come in different forms. right? You can suspend a gas in another gas. You can suspend a gas in a liquid, a gas in a solid, a liquid in a gas, all combinations. How do we tell whether we have a colloid or a solution? I mentioned the particle size. Particle size ranges between 1 and 1,000 nanometers. Right, so with a microscope, you can see some of them. I'll come back to this just a minute. Oh, no. I thought I had a picture. All right. So how do we tell a solution from a colloid? Well, let's say we have this is a solution, and this is a colloid. And you have a bright light right here. Shining through that beaker of the solution. If you position your eye right angle, you will not see the beam in the solution. But in the colloid, you will see the beam. The reason is there are no particles here of sufficient size to diffract the light, to bend the light so that you can see it. Over here, the particles are big enough, the light hits those, bounces off, and you can see the beam. This is called the Tyndall effect. And we're going to use that. I think we're going to use that. Yes, we're going to use that when we titrate a substance and the product is silver chloride, an insoluble colloid. And it'll help us determine the endpoint easier. But we'll talk about it more later. Okay, so these are different types of colloids, and you may want to look at them and see, what do we call these? If the dispersing medium is a gas, we can't call it a solvent because it's not a solution. So the dispersing medium or the suspending medium is a gas. The major part is a gas. And the dispersed substance is a liquid. That's an aerosol. Or we experience it as a fog. So when you're driving through a fog, you're driving through a colloid. If we have a solid suspended in a gas, then like smoke or even bacteria, that's also an aerosol. If we have a gas suspended in a liquid, that's a foam, like soap suds, whipped cream, shaving cream. If a liquid is in a liquid, then we call that an emulsion, right? Like mayonnaise or milk, right? Homogenization of milk makes the particle fat so small that it stays suspended. It doesn't separate as the cream. So if you want to make cream or butter, then you need raw milk. That way it won't be homogenized. And the way they homogenize it, I mean, it's just brute force. They take raw milk and they push it under very high pressure through a stainless steel sieve with very small holes in it. And it breaks the fat particles up into very small, out comes homogenized milk. Then they send it to the pasteurizer. If you suspend a solid in a liquid, that's a sol, not an aerosol, that's a sol. And that's, for instance, a gelatin or a clay or a paint have solids suspended in liquids. A gas suspended in a solid is like a marshmallow, right? It's a solid foam. It's like a foam. It's a gas in a liquid is a foam, a gas in a solid. We have to distinguish it. We call it a solid foam. And you see these ceramic bricks, right, that are heated to red hot, and somebody reaches in there and grabs it with their fingers. The heat capacity of those solid foams is very, very low. So the temperature can be high, but there's not much heat there. So you don't run the risk of burning yourself. Liquid in a solid is like cheese and butter. That's a solid emulsion. So a liquid in a solid is a solid emulsion. A liquid in a liquid is just an emulsion. And then a solid in a solid is a solid salt. Ruby glass. Ruby glass was the original central component of the first lasers. Okay. Now, what happens? A colloid can be destroyed. So when we mean destroyed, that means that the colloid is no longer suspending. In other words, anything that's suspended in the colloid will settle out under the influence of gravity or centrifugation. So one of the ways to do that is to make the particles bigger, right? Instead of spreading them out and letting them interact with the kinetic energy of the dispersing medium, you draw them into a more compact form so that they can't be suspended. Their density increases. And there are a number of ways you can do that. You can heat them, or you can add an electrolyte, right? And most often, these procedures are used to remove proteins and polysaccharides from their colloid form. All right, that's it.